Before we dive into actually practicing the assignment, let's review a little bit more about what a t-test is. So a t-test is a statistical procedure that allows us to make a decision about the null hypothesis when the population variance is not known, and that's the case most of the time. Remember, we don't have access usually to the entire population. So what we do is we take a sample of that population, preferably a random sample of that population, and we use sample statistics to stand in for population parameters. So we'll use the sample mean to stand in for the population mean. And we'll calculate a sample standard deviation to estimate the population standard deviation. Okay, so, but we use a t-test when we don't know what the population variance is. So the overall problem here is that in order to accept or reject the null hypothesis, we must know the population variance, and if we can't know it, then we have to estimate it. And so as a result, a t-test is very much like a z-score for a sample mean if you recall back to your undergraduate days. And maybe you didn't take statistics as an undergraduate, so don't worry too much if you don't know what a z-score for a sample mean is. The main difference is that we use a z-score when we know or are given the population variance. And in contrast, a t-test requires that we estimate the population variance from the sample variance. So those are some technical foundation points for a t-test. This is when we would use it relative to a z-score. Now, the most common version of a t-test that you'll see in the literature, and this is probably the most frequently reported statistic other than perhaps ANOVA, but I think t-test is probably more frequent, is an independent samples t-test. And it's the most common version. For example, if you had two groups, males and females, intervention group versus control group, and so forth, an independent samples t-test may be appropriate. So what would happen is that all participants would complete a measure of interest, and we might call that the dependent measure, which is assessing a dependent variable. And then we look for differences in the means between the two groups. Now, what kind of difference? Well, the difference in the means has to be larger than what we might reasonably expect to happen randomly. Sometimes we will say, more than we might expect from measurement error. But we're looking for a difference that's large enough that we could reject the null hypothesis that the population means are equal. So when we say that there's a statistically significant difference, what we really mean is that the mean difference is large enough between these two groups so that we can reject the proposition that the group means are equal in the population. Okay, so we're looking for big mean differences between groups. Now, this is probably one of the more confusing parts of statistics. And we say, well, we're looking for big mean differences. What does that mean? Well, it's a little hard to define what a big mean difference is because whether or not a difference between the means is big depends on how much variation we see within the groups. Okay, so here's an example. Here's a treatment group and a control group. Now you'll notice that each of these groups has its own distribution. So the control group is this black curve right here, and this is a normally distributed set of scores, so it looks like a bell-shaped distribution. It will have a mean, and the mean is represented on this vertical line right here. Okay, and now if the treatment group was in fact perfectly equal to the control group, this blue distribution, which is also normally distributed and has its own mean, which is the red dots, this blue distribution would completely overlap this black curve, right? So the blue and the black, you wouldn't see any difference between these two. And the mean line here, the line representing the mean, would overlay right on the black line here. So that would be a case in which there is no mean difference between the groups, and the shape of the distribution representing the variation of scores is exactly the same between the two groups. Now, if that were the case, we'd say, hey, there's really nothing to distinguish this treatment group from the control group. So we're going to conclude that they are probably drawn from the same population. Okay, there's really nothing here that makes us think that these groups are any different in the population. This would be akin to saying, well, the treatment didn't work, and if the treatment didn't work, then the control group and the supposed treatment group really are still drawn from the same population. It's a population of individuals who haven't been treated. Okay, so but now imagine if the treatment did work, whatever that treatment is. Okay, imagine if the treatment did work. What would you expect to see? What you would expect to see is that these means would not be the same on a dependent measure, right? So the dependent measure is our measure of interest. It's our outcome measure, and it should be relevant and sensitive to assessing a treatment effect. So if there's a treatment effect, then the means are going to be different. And the stronger the treatment effect, the more we'd see this red line right here moving out toward the tail of the control group distribution until, let's say, that red line came all the way over here. Now, importantly, the shape of the distribution might not change. This bell curve may not change in shape at all for the treatment group, but the mean has shifted, say, way over here to the right. So much so that the mean for the treatment group now resides in the tail of the distribution for the control group. Okay? So now we're starting to think, these two groups look like they come from different populations. Why would we say that? Well, the control group distribution looks like, it has to be a group of individuals who were not treated. The treatment group, though, doesn't look like the control group anymore. So we might start concluding that's a group that looks like, it looks pretty different from the control group, and it looks like it's drawn from a population of individuals who have been successfully treated. Okay, and now you're beginning to wonder, okay, given how big we see the difference in the means, and given how much variation we naturally see within groups, is this difference large enough for us to reject the idea that we're looking at the same populations for these groups? They may be very different populations. In fact, the control group is drawn from a population of individuals who have not been treated at all, and the treatment group is drawn from a population of folks who were treated effectively. So the general form of the independent samples t-test goes something like this. In the numerator, we always see differences, right, in these statistical tests. So in the numerator, it's the difference in the means. We're just comparing, say, control group to intervention group, men to women, okay, as long as they're independent of one another. Differences in the means. And then in the denominator, we have what's called the standard error of the mean, which we're not going to spend a lot of time explaining what that is. You don't really need to know the technical description of standard error of the mean, but it pretty much comes down to how much variation we find within groups. And that creates what we call a ratio, the t ratio. So that t ratio, if it's large enough, and the way it gets large is by increasing the size of the numerator. Okay, if it gets large enough and surpasses a critical value, that's when we reject the null hypothesis. You might say, well, where do we get that critical value? Well, if you recall from statistics, we get it from a table, a t-table. We're not going to do that for this class, but that's where you would get it. Okay, so the most common versions of the test also include, other than the independent samples t-test, a dependent samples t-test, sometimes called a matched samples or a paired samples t-test. And in this case, there's two types. The first type is what we call a within subject repeated measures t-test. Okay, the most common type of t-test that you see like this is, say, when there's a pre-test followed by a post-test. So we give the measure. Okay, like in our assignment that's coming, it might be a Beck depression inventory. Okay, and we give that measure prior to treatment. So this is outcome assessment at time 1. And then we give them the first version of treatment, which would be X. And then at the end of the treatment, we measure them again on the Beck depression inventory. So that's our outcome measure 2. This is, by the way, familiar design notation to express how experiments might work. So OXO, O being the outcome, X being the treatment. Okay? Well, this is a repeated measures because the same person's getting the same measure twice. Okay? So that'd be the first type of dependent samples test. And the other is a matched samples. And in matched samples, you have participants that are related in some way. They're not completely independent of one another. And examples would be husbands and wives, fathers and sons, mothers and daughters. And then you pair them together, give them the outcome measure, and you're looking for differences between the two scores. So you if I was paired with my mother, for example, and we were both completing a survey, she would get a score on the survey, I would get a score on the survey, and it's the difference that would reflect, that would ultimately become the data for the analysis. Okay, the null hypothesis is that there should be no differences between myself and my mother on the outcome measure, and that should be true for everyone. That there's no relationship in the data there. So the example of the research question, though, is there a significant difference in emotional commitment between men and women in their marriage? You would have a husband fill out a survey on emotional engagement and a wife fill out the survey on emotional engagement. If it's the case that there's no difference between men and women, then the average difference score between men and women should be 0. Okay, so let's review really quickly. When do we use a t-test? When there are only 2 means to be compared, so we have 2 groups. And if the research subjects are not related to one another, we use an independent samples t-test. If the participants in the 2 groups are related in some way, they're either the same person measured twice, or they're different people who share some form of relationship and it makes sense to pair them together, then we use a dependent samples t-test. The last thing I want to talk about is what's called parametric assumptions. In statistics, we have to satisfy certain parametric assumptions before we can legitimately conduct and interpret a test. Now, we're going to be looking at one of these types of assumptions when we go through our analyses, and that's homogeneity of variance. But there's actually several assumptions that are typical to what we call parametric tests, and these are important especially for tests that involve null hypothesis testing, and which are called inferential tests. So homogeneity of variance, basically, to satisfy this assumption, we have to conclude that there is no evidence that the population variances are significantly different for the 2 groups. Okay, this doesn't really speak so much about the bell-shaped distribution. It's just that the variances for the 2 groups can't be hugely different from one another. And I could, spend an hour probably showing you why that becomes a problem. And if anyone's ever interested, I have a couple of good examples why that becomes a problem. But what will happen when you run your SPSS analysis is that before it actually gives you the t-test results, it's going to provide you results on what's called Levene's homogeneity of variance test. In this case, we are not looking for a statistically significant finding. We're looking for a finding that is not statistically significant. As long as the test for homogeneity of variance is not statistically significant, what we conclude is that there's no evidence at this point in time that the population variances are significantly different from one another. Okay? And just real briefly, why is that important? It's because when you do a t-test, you actually pool the variances from both groups together. And if the variances are really different from one another, that pooling doesn't actually add a whole lot. It can actually create the possibility for some type 1 errors in the null hypothesis testing. So that's the short answer to it. Okay. The second parametric assumption is that the characteristic is normally distributed in the population. So whatever it is that we're measuring, we have to be reasonably convinced that it is normally distributed in the population. A normal distribution is not the only kind of distribution that we can have, but generally speaking, it's the most common type of distribution. Now, what's really important here to realize is that when we do a t-test, we could talk about the characteristics distribution in the population, but actually when we run the t-test, we base those results off of what's called a sampling distribution. Okay, and the sampling distribution is a little bit different from the distribution of the variable in the population, and something you should know is that the sampling distributions tend to be normally distributed even if the characteristic is not necessarily normally distributed in the population. Because of that, and here's the bottom line, this is all you need to know, statistical tests like t-tests in ANOVA tend to be what we call robust to violations of normal distribution. So even when a characteristic is not normally distributed in the population, the t-test and ANOVA results tend to be accurate, okay, in terms of estimating population parameters and whether or not there are statistically significant differences and so forth. So it's generally not an issue that we encounter too frequently. A third issue, and it really depends on the test that you're running, is independence. That the group members have to be independent of one another. You don't want contamination of subjects across groups that could affect their scores. Of course, with a paired samples t-test, dependent t-test, they're not going to be independent by definition, but the math takes some of that into account. We also have to see interval or ratio scale of measurement. Real briefly on that, it simply means that we can attach numbers to points on our measurement scale and that the distance between the points is equal. Okay, so when I give a survey and it's a 5-point scale, we're assuming that the distance from 0 to 1, from 1 to 2, from 2 to 3, and so forth, pretty well matches psychologically how people think about the distance on the scale. That's a tougher one. It's been a debate for a long time. I don't think that's ever really going to get resolved because some people will argue that really what you have in psychology is a lot of ordinal scale measurement, which involves just rank ordering rather than interval or ratio. And then lastly, random sampling, that we're randomly sampling from the population. With some tests, we don't necessarily assume random sampling. But with, say, an independent samples t-test, we're assuming that the data are actually being randomly sampled from the population. That's actually more of the exception than the norm. If you think about it, psychology and a lot of psychological research has been, built off of the backs of the college sophomore getting extra credit for research participation, and they were certainly not random individuals from society participating in an experiment. So there are actually frequent violations of some of these assumptions. Part of the problem is we're not exactly sure how important those violations are. Some of these things we can study statistically and psychometrically, and we can understand how important they are. Other things are more design oriented, and it's a little bit difficult to understand how significant those problems might be. Okay, so that's just a review of t-tests. The good news is we're going to run both of these, both dependent and independent samples t-tests. And now off to do some data entry.